In this video, we're going to be talking about 5.8, which is inverse trigonometric functions, the integration techniques for them. Talked about these in Calculus 1 as some of our basic forms, but let's go back and refresh because not everybody talks about these inverse trig integrals in Calculus 1. So let's integrate functions whose antiderivatives involve inverse trigonometric functions. Let's use the method of completing the square to integrate a function. And let's review the basic integration rules involving elementary functions while we're at it. So let's go ahead and look at theorem 5.19 from the textbook, which tells us how to integrate these integrals that give us inverse trigonometric functions. So integrals involving inverse trigonometric functions, let u be a differentiable function of x and let a be a positive constant here. Then the integral of du over the square root of a squared minus u squared is equal to arc sine of u over a plus c. Notice there's no multiplier in front of the arc sine here. That's what makes this one different. And you're looking here for this integral of a squared minus u squared. It's going to start with a constant and then subtract the square of a function of x like that. That's how you're going to know you're going to get arc sine of u over a. It's okay to write this as arc sine like this. We just don't like this notation as much because people get the -1 confused with the reciprocal. So we usually write out arc sine like this so that you know that it's the inverse sine function. And integral like this of du over, notice there's no square root here. It's just a squared plus u squared. This is the only one with a plus sign in it, and there's no square root here. Is going to be 1 over a is going to be there this time. Arctangent of u over a plus c, and then integral of du over, watch out, there's an extra u there, square root of u squared minus a squared. So this time it's the function of x that's being squared minus the constant is going to be over here that you're going to need to find the square root of that constant. This will be 1 over a arc secant. And very important here that you use this absolute value bars here in your answer for the arcsecant rule. So it's arcsecant of the absolute value of u over a plus c. All right, we're going to get some examples here to try out. So the first one is pretty basic, that it matches the form of number 1. And we just need to say that that is a squared is equal to 4, which means a is equal to 2, and u is equal to x there is what's being squared. So du is going to be equal to dx. So this is in the form of du over the square root of a squared minus u squared is equal to arc sine of u over a plus c is going to be arc sine of u is x, a is 2 plus c. So if we change that up just a little bit, and we know we would make this x over the square root of 4 minus x squared dx. We would no longer have this type of a substitution because we don't have something squared and the derivative of that something that was being squared in the top, we now have, oh, something inside of the square root sign that I can take the exact derivative of that thing and fix it like this. So this is -1/2 u to the -1/2 du. And so this is an old type of integral. If you get one of those on the test, don't let your teacher trick you. You should know how to do all of your Calculus 1 integrals and Calculus 2. It's fair game to put a mixture of Calculus 1 and Calculus 2 integrals on your test and expect you to know how to recognize what's Calculus 1 and what's Calculus 2. So if you get the ugly thing as an inner function and you get the top as something that's 1 degree less that you could take the derivative, it's a basic u du substitution. So you're going to want to make this a -1/2 times u to the 1/2 over 1/2 plus c. So these will cancel. The 1/2 and the -1/2 and the 1/2 will make a -1. U to the 1/2, so that's going to be square root of 4 minus x squared here plus c. And there you go. So if we'll have some other examples down here to look at in just a second, where we'll try something else where we do x plus 2 over the square root of 4 minus x squared. But before we do that, let's look at an example of number 2 here, where a squared is equal to 2. Yuck, that means a needs to be the square root of 2. And u squared is equal to 9x squared, which means that u, I need to think of that as 3x. So du is going to be 3 dx. So now this is in the form of integral of, well, I need a 3 dx, so that needs to be a 1/3 there. And this is going to be du over a squared plus u squared is 1/3. And then we have 1 over a arctangent of u over a plus c. All right. Now we get one that looks like number 3, or pretty close to it. So I'm going to start with the 4x squared needs to be u squared. And that means that my u needs to be 2x and my du needs to be 2 dx. So I'm going to multiply by 2 over 2 here. And that gets me into the form of, let's see, a squared is 9, so a is 3. So this is going to be du over u square root of u squared minus a squared. That's going to give me 1 over a. I should have given you the formula here before I wrote the answer. So this is 1/3 times 1 over a arctangent of u over a plus c. And so this is going to be 1 over 3 root 2 arctangent of 3x over root 2 plus c. This one is 1 over a times arcsecant of the absolute value of u over a plus c. So 1 over a here is going to be 1/3 arcsecant of the absolute value of 2x over a is 3 plus c. That 2 doesn't need to stay inside of the absolute value bars. I can take the absolute value of 2. So this is 1/3 arcsecant of 2 absolute value of x over 3 plus c, like that. Now let's talk about this last extra example here. And we get a lot of these in calculus 2, where we need to split up the integrals here. So we're going to split this up into this and this, where this is going to be a basic u du substitution. And this one is going to be an arc sine rule. So if u here is going to be 4 minus x squared, du is going to be a negative 2x dx. Need to make this a negative 2 and a negative 1/2 to fix that. This can be a negative 1/2 of u to the negative 1/2 du. I've actually already done this one, I think. I might have done it with the number 9 instead of the number 4. This one here, I'll use a t substitution instead. And I'll say t is equal to x and dt is equal to dx. A is equal to 2 because a squared was equal to 4. And this is 2 integral of dt over square root of a squared minus t squared, like that. It's going to give me negative 1/2 u to a positive 1/2 over 1/2 plus 2. And then this is going to be arc sine of t over a plus c. This is going to be negative square root of 4 minus x squared plus 2 arc sine of x over 2. Going back up to my list and back substituting that t is x and that a is 2. And that sum there, I might want to write that as subtraction, just so you don't miss that negative sign. Either way here, this is our final answer. Let's talk about completing the square. We have to do that quite a bit in these trigonometric, these inverse trig integrals. So let's look at x squared minus 4x here, and then put the plus 7 on the outside here. This is a dx. So remember that if we have something in the form of x squared plus 2ax plus a squared, that this breaks down into x plus a squared. And if we have x squared minus 2ax plus a squared, that breaks down into x minus a squared. So if we find half of this middle number and then square it, we'll get what's called a perfect square trinomial. On the left-hand side that we can factor into a perfect square on the right-hand side, and that will help us get this form of one of these inverse trigonometric intervals here. And I'm looking for that because I can't take the derivative of an x squared polynomial that's in the denominator, letting that be u, and just get a dx on the top. I would need something with an x up there. So because of that, I'm looking for a form that is inverse trig. Probably this looks like it's going to be an inverse tangent, an arctangent, because I see no square root involved here at all. So I'm thinking arctangent. So half of the middle number is -2. -2 squared is a +4. So I want a +4 here. I can't just go around throwing in +4 without also balancing it out with a -4. So this is going to make this x -2 quantity squared. 7 minus 4 is a +3. Get a dx. So our u is what's inside here, x minus 2, making our du equal to dx. Perfect. We know our a squared is 3, so a has to be the square root of 3. So that means that we have du over u squared plus a squared, which is 1 over a arctangent of u over a plus c. This is going to be 1 over root 3 arctangent of x minus 2 over root 3 plus c. So that's it for, nope, that's not it. Let's do another one. Let's do a definite integral this time. So let's find the area of the region bounded by the graph of f of x is equal to 1 over root 3x minus x squared. The x-axis and the lines x equals 3/2 and x equals 9/4. So if we looked at that, we would have stick 3/2 in here. That's 9/2 minus 9/4. It's going to give me 18/4 minus 9/4 is 9/4. Square root of 9/4 is 3/2. This is 2/3. So 3/2, 2/3 is here. Then we have x is 9/4. So 27/4 minus 81/16. 4 over 4. It's going to give me 108 over 16 minus 81 over 16 is 27 over 16 is going to be 3 root 3 over 4. So this is 4. I take the reciprocal of that. That's 4 over 3 root 3 is 4 root 3 over 9. And it's not quite 1. A little closer to 1. 9/4 is 2 1/4. And a little closer here to 1. And we are in this area right here. Something like that we want to find. Okay. So didn't really need to do that to set this up, but just see that 3/2 is the lower bound. 9/4 is the upper bound. I have this function here, and I'm integrating with respect to x here. And so I'm going to try to complete the square, but I have a negative in front of my x squared, and I don't like that. So we'll do this. Negative x squared minus 3x. And we'll deal with what's going to be on the outside there in just a second. So half of the middle number squared is going to be plus 9/4 in here. And then I just actually subtracted 9/4, so I need to add 9/4 on the outside to balance it out, because this negative times that 9/4 was a negative 9/4. So the opposite of that is a positive 9/4. Gets added on the inside there. So this is going to be 3/2 to 9/4 dx. Then let's rewrite this as 9/4 minus x minus 3/2 quantity squared. Now, if you had wanted to do some arithmetic here before you get started, you can. I don't think it helps you to multiply by 4 here at all. So let's just leave it like this and say that our u is equal to x minus 3/2. Du is going to be dx. Our a squared is going to be 9/4. So our a is equal to 3/2. That gives us the integral. Just we're going to be using this rule here. Du over square root of a squared minus u squared, like that. So we're in this world right here with arc sine is going to be a squared minus u squared is going to give us arc sine of u over a plus c. So that's the idea that we're thinking of, but we're going to make that definite. Let's make sure we have all the pieces parts correct. So 3/2 x minus 3/2, that's dx, that's good. Yes, so we're going to get arc sine of x minus 3/2 over 3/2. I'll clean that up in just a second. We're going to evaluate that from 3/2 to 9/4. So that's going to be arc sine of 0 minus arc sine of 9/4 minus 3/2. So that's going to be 3/4. 3/4 divided by 3/2 is 3/4 times 2/3 is 2/4 is 1/2. Sine of 1/2. So that's going to be arc sine of 0 is 0. Arc sine of 1/2 is pi over 6. So this should be a negative pi over 6 for our answer. Let's make sure that that's right. We're told to find an area. And I can't have a negative area. So let me check my work here. I did these backwards. Upper minus lower. Right. This is pi over 6 minus 0. And this is pi over 6. Right. So we need to stick in the 9/4 first, which gives us the arcsine of 1/2, and then stick in the 3/2, which gives us the arcsine of 0. I'm done. And we'll do more problems like that are some applications later. When we come back next time, we will be looking at topics from chapter 7. So see you for the next video.